Well, well, good morning. Please tell me what you think. Check. Some people still not here. I want to thank everybody who sent a feedback, and I like reading your feedback. I also like giving a feedback to your feedback. First, when I read your feedback, I feel always a sense of relief. My handwriting is not the worst. There is worse. You can look them up. They all know Blackbird, no names. So, well, a couple of things very quickly. Labs, a little bit difficult. Labs, great. Labs, pointless. Labs, very helpful. I can go on and on. So this is, again, just an illustration of the fact that everything is relative. What's good for one person seems not so good for another person. And just word of advice, if you enter the lab and you think, I'm going to hate it, you will be hating it. So since you cannot do anything about it, even I can't do anything about it. In order to graduate from the course, there is a minimum number of labs everybody has to do. It's just easier to think about it differently. Otherwise, you're going to feel hate for like 3 hours straight. Not good for your just general health. Plus, you can talk to other fellow students, and maybe they would tell you what they find useful, some elements which could be useful for you too. Now, teaching fellows grade, not so grade, bad. Well, as I told you before, all teaching fellows are equal, but some are more equal than others. I give you exactly the same instructions, and still you have different outcome. I give exactly the same instructions to teaching fellows, and of course, based on their experience, their background, they work differently, and only you can do something about it by asking more questions and pushing them for helping you more actively. I wish we wouldn't have classes on Wednesdays. Me too. And let's take a look on the distribution. In your feedback, some of you also addressed the exam, and the similar distribution, by the way, I didn't ask question number 3 yet, so please don't do that. Different people addressed the exam and assessed it differently again. Fair, harder, no one said easier, except a couple of students now. So again, it is really, really relative. It depends heavily on background and internal feeling, attitudes. I'm still in the fog. 2 students still in the fog. Well, no comments. Just get some more coffee. That helps. A very common distribution, nothing really pops out from last year or a year before. The average is very close. And the fact that about 2/3 of the class finished the exam before the time, and about 53 out of now it's 89, I think, students get the grade in the range between A and minus. 10 years ago, a faculty with this grade probably would have been fired. Too good to be true. So what I see is only 2 options. Number 1, you are satisfied with your grade. In that case, probably just keep doing what you've been doing. That worked for you. If you are not satisfied with your grade, you probably need to make adjustments in your preparation strategy, in your learning approach. Maybe shift more time to office hours or something else. And see me if you have any questions. Do you have any questions? All right, let's go back to physics. So that's what we're going to study for 2 weeks before the next exam. We start from the homework is available, and again, the actual deadline set this time, the same for all parts of the homework. But I strongly recommend not waiting until the deadline looms on you. Do as much as possible before, and maybe leave some extra time for the practice problems, because that helps. So we talked about an official definition of friction, and we know by definition this is a component of an actual contact force. All right. I hope these people didn't quit just late. But I need this space for my small experiments. You can pick it up later if you need. So we saw the experiments with the ramp, for example. it's not moving. If I would be able to get rid of the friction, to eliminate friction completely, like having a cart with almost frictionless wheels, even at a small angle, it would be moving already. But it's not moving now, which means friction prevents it from moving. So when friction is acting, but the object is not moving, that's what we call static friction. When friction is acting and the object is moving, that's what we call kinetic friction. And friction is a little bit tricky force. For example, let's talk about static friction. Definitely it's supposed to depend on the angle, because when the angle increases, as we know from the past, the component of force of gravity parallel to the surface also increases. It goes from 0 to eventually mg. And because the object is in equilibrium, that means net force acting on this object right now is supposed to be equal to 0. It means force of friction, which prevents it from moving, must have exactly the same magnitude as the parallel component of force of gravity. And because this component changes, that means force of static friction changes. But it cannot change, well, infinitely. At a certain point, it has to start sliding, which means the force of static friction has a limit, the maximum value. It's easier, of course, to start from pushing and pulling objects on a horizontal surface. In that case, we don't have to think about angles, sine, cosine. Here, I can attach, we can call it a spring scale, dynamometer, force meter, device which measures applied force. I pull on this hook and I can see the magnitude of the force. And right now the magnitude of this force is not 0. But the object is not moving. Why? Well, because force of friction prevents it from moving. But if the object is at rest, friction must have exactly the same magnitude as the tension in the string. If I increase the tension, friction must increase, but it's not going to happen infinitely. At a certain point, it starts moving. So there is the maximum value static friction can provide to this box from this surface. It depends on the surface. I can oil it up, and of course, in that case, the critical value decreases. What else can I do? I can add some mass to it. Actually, now I'm going to have to use a different scale. Well, I know that, but you don't. So let's see what's going to happen now with this. I push, nothing. So 20 is not enough. So that's why I have to use a different scale, which measures up to 50 newtons. And here. So now the critical force is larger than before. And if we do very accurate experiments, because I doubled the mass, we can see the maximum force of static friction also doubled. And such experiments tells us that friction actually are proportional to the normal force. Normal force might depend on the angle. Normal force in the elevator might depend on the acceleration. And if we run all the experiments on friction, we will figure out that, turns out, if we use the same surfaces, normal force always proportional, and frictional force always proportional to each other. And that leads to a definition of coefficient which relates these forces. So this is the reason for friction. No matter how we feel the surface, it might feel very smooth. In reality, it's never absolutely smooth. And even if it would have been, still in that case, molecular attraction would hold objects together. So there is always contact force. And those little teeth, like tiny gears, they're responsible for the resistance. And this number, which is a ratio between the actual magnitude of the force of friction and the normal force, has a name, the coefficient of static friction. And this coefficient depends on the condition between the surfaces in contact. If it's wood and wood, that would be one number. If it's wood and glass, that would be another number. Ice and paper, the third number. And of course, you always can Google the value. It's been measured for all pairs of surfaces. But in our problems, this number either given or is an unknown which we have to solve for. Of course, so this is a question for you. Now if we talk about kinetic friction, we can repeat the same experiments. We just have to make sure the object is sliding with a constant velocity, like this one. If velocity is constant, acceleration is 0, that means net force is again 0, as we know. And if net force is 0, that means tension and friction also have the same magnitudes. So this is how we measure kinetic friction. And an official definition of a coefficient of kinetic friction, again, is a ratio. The magnitude of the force of kinetic friction divided by the normal force acting on this object has a name, coefficient of kinetic friction. And the question for you is, what do you think about the unit of the coefficient of kinetic friction? Well, the unit of coefficient of static friction, of course, will be the same. They share the unit. So this is a review lecture 1, unit analysis. We can repeat experiment again. If we double the mass, which in this situation means we're also doubling the normal force. And if we make it move now with 0 acceleration but constant velocity, we can see the force also doubled. And again, such experiments tells us that friction and normal forces are directly proportional, and that leads us to the introduction of this new physical quantity, the coefficient of friction. Two forces, two coefficients. Yeah. Static friction means we have to use coefficient of static friction. Kinetic friction means we have to use the coefficient of kinetic friction. They're not usually equal to each other. If you ever moved heavy thing like a refrigerator, you know that make it into a motion from rest is harder than keep it moving afterwards, usually, because coefficient of static friction usually is slightly larger than coefficient of kinetic friction. Let's see what you said about the unit. So 1 or 5, 1 or 5, 1. 1 is wrong, because unit analysis tells us the unit of the coefficient should be equal to the unit of force divided by the unit of force, which means a Newton over a Newton. So it's getting canceled. So it has no unit. This is a rare situation in physics. Normally, physical quantity has a unit, but this is the case when it doesn't. Now, say, I forgot to mention, probably you know, this is a Greek letter, mu, not mu. Any questions? So far, it's just a definition. Now we got to solve a couple of problems to see how it works. For example, I'm going to give you a minute to draw a Freebody diagram because this problem is about forces. What do we know about forces after the first exam? Everything. So technically, we are not learning anything new except one definition, which is on the screen. We just added one more force to the list of our forces. We knew force of gravity, normal force, general applied force. Now we added one more force. We know how that force is related to other forces. So we just have to follow the same strategy we used before every time when we had to analyze any problem related to forces acting on an object or several objects. It starts from a diagram, Newton's second law, and we just follow the logic and see where it will lead us. So in this situation, we know that there has to be a force acting on this box which divides all forces into two different segments regimes. If the applied force is not very strong, the object is not moving. If the applied force is stronger than that critical one, the object begins moving. Well, something in this situation, something like this. We can use the scale as a dynamometer. So when it's easier if the value is larger. So I push and I push and I push, nothing. But when critical force is reached, well, they start moving. That's what we're looking for. Well, by now, everybody already should have a Freebody diagram drawn. And how does it look like? Well, I have to just add the force of gravity, mg, and normal force. And where else? What force should I add? It's already there. Green, large green arrow represents the applied force, and we are looking for that force. So what's missing? Friction. So what took you so long? We talk about friction, so yes. That's it. What do we do about that huge green arrow? We know as every vector it has components. There is a horizontal components, force applied x. Vertical components, force applied y. Now, do you think the normal force is equal to Newtons? No, because as we remember, when we kind of adding some push from above, that increases the normal force. So you see, again, we just have to repeat exactly the same reasoning we used before, which means we cannot erase from the memory everything we've learned before the exam number one. because we have to use it again and again. We have to reuse that. So, well, let's start writing x and y components of the Newton's law relative to the x component. Well, the word minimum means that the horizontal component reaches that critical value, and the box on one hand still is at rest, but on the other hand begins moving. You know. What does it mean? It means at that critical moment, the x component of the applied force should reach not just force of friction, should reach maximum value of the force of static friction. Because if we add just a fraction of a force, a fraction of newtons, that's it. It starts moving. And we have no other forces pointing horizontally. Now, in the vertical direction, we have normal force minus vertical component of applied force minus, well, gravity equals, bless you, 0. This is just the straightforward application of the Newton's second law. But now we can add one more equation, which is on the screen, but we don't like fraction bars, so we can rewrite it. Maximum value of the force of static friction should be equal to the coefficient times normal force. That's not the Newton's second law or first or third. This is basically a definition of a coefficient of static friction. We always can write it when we need to relate normal force and static friction. Done in terms of physics. Well, that's the first example on the force of friction, so let's finish it. So what can we write down? Well, first of all, I can solve the equation number 2 for the normal force and use that expression for the normal force here, right? What else can I do? Well, this is the maximum value of the force of static friction, which has been reached at the moment when the object just begins the motion. And wherever I have it here, I should have also in the first equation on the right, because that's the same force. So that tells me that the x component of the applied force should be equal to, now, read my mind. I'm replacing the things mentally. So force of static friction will be equal to the coefficient of static friction times the normal force. But from the second equation, the normal force will be equal to the vertical component of the applied force plus force of gravity, which is 400. However, now we can also relate components with the magnitude, because, as we know, for every vector, the components and the vector together always form right triangle. So the x component should be equal to the unknown magnitude times cosine of 30 degrees. And the magnitude of the y component should be equal to hypotenuse, same unknown force, times the sine of 30 degrees. So now, if we use this geometry, we can rewrite the equation. F times cosine 30 equals, the coefficient is a given number, 0.8. That should be equal to F times sine 30 plus 400. And now I'm going to stop. The rest is a standard calculation when we have to solve an equation with only one unknown left in it. You have to open the parentheses, multiply everything by a coefficient, move it over here, combine two terms with the unknown. The unknown is a common factor, pull it outside parentheses. That's a very good exercise, so you should do it. So now I can write math is almost done. Now, of course, a similar situation, but related to the force of kinetic friction. The box is moving, but the velocity remains constant, which means immediately acceleration is supposed to be 0, which means net force has to be 0. So I'm going to do it faster now, because nothing mathematically is different from what we just did. Same geometry, same conditions. The only difference is, in the previous problem, we knew the coefficient, we were looking for the force. Now we know the force, we are looking for the coefficient. From the mathematical point of view, there is no difference at all. So, again, oops, that's mg. That's normal force. It has to be the force of friction. Now it's a kinetic friction. And we now can calculate the components. The x component should be equal to 100 times cosine 30 degrees. And the magnitude of the y component should be equal to 100 times sine of 30 degrees. And again, acceleration is 0 because velocity is constant. And we know that because we've learned it before. So the Newton's second law tells us if x should have the same magnitude as F friction, only two horizontal forces, and they cancel each other out. Relative to y-axis, we can write immediately that the magnitude of the normal force should be equal to the magnitude of the y component of the applied force plus force of gravity. And the third equation relates frictional force and normal force. So again, mathematically, nothing new. What do? Very quickly. 100 times cosine 30 should be equal to frictional force, which is the coefficient times normal force, which is the vertical component, which is 100 times sine 30 plus 400. This equation even easier than the equation we had before, because now all we have to do is just divide two numbers, 100 times cosine 30 over 100 times sine 30 plus 400. That should be point something, small number. Done. So again, it's instructive to remember, if you read a problem and there is something related to a word force, that immediately forces you to use everything you learn about forces. Freebody diagram, Newton's second law, plus sometimes you may need an additional expression which relates some forces acting inside the system. All right. you pushed the box. Pushed the box means you acted almost instantaneously. This what happened. Pushing means this. Pushing means you've been applying the force for a long period of time. Pushed means this. Pushed, kicked, burst. Yeah. Just very quick interaction. And after that, what's happening? Well, it slides and eventually stops. That's what is happening. After the push, the speed of the box was equal to 15 meters per second. Eventually, the speed of the box becomes equal to what number? 0. And this is, we need to calculate the distance traveled. First of all, this picture already tells us that we know a lot about this situation. Yeah. Initial velocity, final velocity, distance traveled. Those are variables which usually are part of a bigger picture, which also involves a couple of other physical variables. What could I add to the list of physical variables to this list? So initial velocity, final velocity, where else? What do you think? What other variable is a part of the connection? What do you think? When velocity changes? Someone was whispering. Say the same word, please, but louder. Whoever was whispering, I don't know who. I was watching that gentleman, but I was listening to your whispering, so I knew you said it, so please just say it out loud. No, that's not what you said. Why did you change your mind? You said acceleration. I heard it. Well, someone, I don't know who. Acceleration, and there's one more variable which also belongs to the same list. What is it? What do you think? Velocity initial, velocity final, acceleration. Yes? Time. At this point, you shouldn't be thinking about it. It should be like knowing your own first and second name, or your friend's first and second name, if you know. So these variables are related together always. So this is a complete list which describes motion with constant acceleration. They're all related. And there is another list of variables which includes coefficient of kinetic friction in this situation. And coefficient is related to force of friction, of course. And if we talk about forces, of course, Newton's second law relates forces and mass, and also what? Acceleration. So this variable, acceleration, becomes a bridge between one set of variables which we used to use to describe the motion, just how it's happening, and the second set of variables which we used to describe why is this happening. Yeah, that's what we call kinematics. That's what we call dynamics. This type of reasoning, just listing all important quantities without even asking, do we know, do we need to know, it doesn't matter. This type of reasoning is what we call thinking as a physicist. Well, if we talk about motion with constant acceleration, we can immediately throw in set of equations, again, without thinking. Final velocity equals initial velocity plus acceleration times time. X equals x initial plus initial velocity times time plus 1/2 acceleration time squared. There's a third equation which has no name, that's its name. In final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. That's all we know about motion with constant acceleration. What do we know about forces? Well, first we have to do what we have to do, meaning we have to draw a diagram, free body diagram. Free body diagram ideally is supposed to also show the acceleration. So acceleration is a vector. As any vector, it has a direction. And how do we describe directions? We use words like left, right, up, down, northeast, southwest. So please tell me, what is the direction of acceleration of this box while the box slides down to the right? How do we call it? No, I didn't say negative. I said left, right, up, down, north, south, east, west, left. But the component of the acceleration will be negative. We talked about it. Saying acceleration is negative is outdated. It's out of the fashion anymore. We don't say that anymore. We say acceleration has a negative component relative to the positive x direction. Of course, naturally. X-axis points to the right, and acceleration has to point to the left because the object is slowing down, and we know that because we learned it 2 weeks ago. And well, if we use the y component of the Newton's second law, it only tells us normal force must have the same magnitude of the force of gravity. But unfortunately, in this situation, we don't know the mass. It's not on the screen. So all I can write for the normal force, it equals m times 10. And if we write the x component of the Newton's second law, we should write what? Do we have any horizontal force directed to the right? Yes or no? Is there any force acting on this box which points to the right? No. Why does it move to the right? Because there was a force. But while the box is sliding, we don't touch it anymore. It's sliding by inertia, and only force of friction acting on it. So how does it point? To the left. Technically, it should have a negative component, and same, the acceleration should have a negative component. So that's the Newton's second law for this box, written relative to the x-axis. Now, again, my favorite statement. I'm gonna, where's my marker? Where's my cursor? Here, okay. I want to do a little bit more math, so I want to insert an extra page. Okay, very quickly. Normal gravity friction. So as we said, normal force equals m times 10. And as we said, magnitude of the force of friction should be equal to m times magnitude of the acceleration. I say magnitude. I don't write those vertical bars which explicitly demonstrate that I'm using magnitude. because I'm lazy. It's easier for me to remember what I'm doing than every time writing those vertical bars. What I also know, so it looks like we have two equations with 1, 2, 3, 4 unknowns. But I also know that the force of friction and the normal force are related. And this coefficient of kinetic friction is equal to 0.4. Okay. 0.4. That's a 4. Any units? Units? No, it has no unit. So just a number. So now what can I write? I can write that force of friction, which is on one hand equals m times a, should be equal to coefficient of kinetic friction times normal force, which is on another hand equals to m times 10. And if I look at this expression, that makes me very, very happy. Why? What can I do? I can cancel the unknown. So this is a very common situation in physics. When you start solving a problem, you read and you feel, we don't know the math. We can't solve it. What should we do? You should believe. Physics is based on beliefs. You should believe the problem is solvable. You should believe you can do it, and you should do it. So what we have in the end is acceleration. 0.4 times 10, 4 meters per second squared. And that's all information we needed to extract from the Newton's law, because now we can go back to our expressions from kinematics. For example, the last one. Oops. What did I do? This one. This expression relates initial velocity, 15, final velocity, 0, acceleration. Acceleration has the magnitude of 4 meters per second squared, and displacement, the only unknown left to calculate. So V final squared equals V initial squared plus 2 times A times, well, delta X or S, same thing for us. So start throwing in numbers. 0 equals 15 squared plus 2 times 4 times S. What does it mean? You,
Oh, it means I get it.
You see what I'm doing? I'm drinking coffee and walking. What does it mean? Something is wrong. You have to find what's wrong and tell me what's wrong and how to fix it. So it's too soon to say, so far you should say, anybody, please jump in. Someone has to say something. Say something. Yes. So how do we unconfuse it? What do we want to make negative? This expression, this equation has three numbers, 15, 2, and 4. 4. All right, now it works. Remember what I said out loud. Magnitude of acceleration equals 4 magnitude. But this expression relates components. Now we're done. Now it's fixed. Now we can just solve it for distance. S equals 15 squared over 2.4, 225 over 8, whatever it. Any questions? So again, to solve this problem, we used much more material from the past than from today. From today, we only used one additional equation which relates force of friction and normal force. Okay, now we're going to talk about other matters. We're going to talk about energy and work first. Hopefully tomorrow we'll start talking about linear momentum. So this is a definition of everything we need to know about energy for now. We know that objects can move, and like this ball, they might slow down, they might speed up. And like in this experiment, when the height increases, it slows down. When the height decreases, it speeds up. Experiments like that tell us that there has to be a connection between, well, how the height changes, how the speed changes. And that connection is given by connection between these variables we call energies. A kinetic energy, by definition, is equal to 1/2 of the product mass times speed squared of an object. And this product, mass times g, magnitude of the acceleration due to gravity, times the vertical component of the position vector, or we can say times vertical coordinate of an object, has a name, gravitational potential energy. When height changes, gravitational potential energy changes. When speed changes, kinetic energy changes. Turns out those changes are related. Now, if we try to calculate kinetic energy or potential energy, we get exactly the same unit. Kilograms times meters per second squared. So this unit has a name, a joule. And potential energy has the same unit. And also, right now, throw it in, this expression tells us how to calculate a work done by a constant force on an object when it's moved from one place to another place. For now, it's just important that the unit is the same. If we calculate the unit, a Newton times a meter, a cosine has no unit, we get again joules, which means again, probably all these variables are related because they have exactly the same unit. And one more, practical quantity, power. That's what we read on every device. Yeah. A power is the amount of work done by a device or an object or a system or a force every second. So this is what we call average power, the amount of work divided by time we spent to do that work. And there's a practical old-fashioned unit of power, horsepower. But of course, in physics, we don't really use horsepower. Engineers use horsepower. In physics, we use a joule over a second, or we call it watt. We're going to use these definitions, of course, all of them later. So question, what do you think about our choices? Kinetic energy, by definition, cannot be negative. It could be equal to 0. When an object is at rest, speed is 0, no kinetic energy. If object is moving, first of all, negative mass doesn't exist, at least so far, and anything squared is positive. So when object is moving, it has kinetic energy, and it's always positive. But gravitational potential energy, by definition, depends on the vertical coordinate. And vertical coordinate depends on vertical axis. And we choose the axis, and that might affect the number for the energy. So the question is, where can we choose the origin of our axis? And what do you say? Where can we choose the origin? The gentleman in the yellow coat. Where? You're only one in the yellow coat. Where can we choose the origin? You have to choose the answer from the list. So where? There's a more general answer for that. Yes, we can. But that doesn't describe all possible options. There's one word which describes all possible options. Which word is that? Cannot hear you. Again, that is a very specific answer. There is a word which describes all possible answers. What word is that? Anywhere. Remember that. You choose the origin. So let's say this is my ruler, that's 0, that's my origin. If I choose the origin here on the surface of this table, what will be the y coordinate of this ball? Equal to what number? 0. And that makes the energy, potential energy of this ball 0. But if the same ball sits on the same table, but I choose my origin here, that's my origin. That's the 0 level. What does make this for the value of gravitational potential and energy? What happens to gravitational potential energy of the same ball on the same place? Negative, because it's below 0. But I can choose my origin on the floor. The origin is there. It's the same ball, same location, but now the y coordinate is positive, and that will make the potential energy positive. So this variable is relative, could be positive, could be negative, could be 0, depending on how we choose the origin. Well, so is potential energy always positive? No. Could be positive, could be negative, could be 0. Now, work. This is a very important definition. When object has been moved from initial location to the final location, to calculate work, we don't care how it's been moved. This variable represents the magnitude of the displacement. That's what it is. We need to know the exact definition of the exact meaning of this variable. And displacement is a vector which connects initial location and final location. So we can measure the magnitude. This variable represents the magnitude of a force work of which we're calculating or measuring. And this is the angle between displacement and the force. That's an official definition of mechanical work done by a constant force. And the force of gravity is constant, for example. So we can calculate using this equation the work done by force of gravity, and we will. But for now, I want to ask you this question. In this experiment, there's an applied force which makes a box move across the table like this. It's not just one force acting on it, of course. There's force of gravity, frictional force, normal force. And the question is, according to this definition, what can you say about the actual value of the work done by the normal force in this experiment? Is it 0? Is it positive? Is it negative? You have to make your mind, enter your choice in the WebAssign. So by now, you don't need the slide anymore. Your answer already is in your brain. So let's see what you say. Let's see. That's the question number 5. So we have 2 competing answers. All right, that's what I want you to do. I told you this time would come, and it did. You have to draw a picture. You have to show clearly in your picture the displacement of the box, the normal force, the angle between the normal force and the displacement. Say something about the value of that angle. Take a picture of your picture and email it to me, to my email address. Try to do it more readable. This is also the way to that's what I forgot. So this picture has to have your name and BUID. That will be also your attendance for today. Yes. Yes, of course. Well, by now, again, you don't really need the screen anymore. And what do I want to do? I want to check my email. And usually I do it on my phone. All right. Okay. I'm starting getting some emails. But of course, I can't give you too much time on doing this. So please, one more minute. Draw a picture. Take a picture of your picture. Please email it to me with your name and ID. Because, again, that's your attendance for today. Because, again, I forgot to place. Yes? I need to see the displacement of this box, the normal force acting on the box, the angle between the displacement and the normal force. Everything else is up to you. If you think some additional features in your picture might help you to answer this question, fine, do it. But what I need to see is the displacement, the normal force, and the angle between these two vectors. A displacement is a vector. A normal force is another vector. Any two vectors always have a certain angle between them, which might range from 0 to 360, technically. So when you have two arrows, there has to be an angle which could be measured or calculated and also photographed. All right. So I could have used the original picture, but I always prefer drawing my own because when I do that, the motion of my hand results in firing up extra neurons in my brain. And I love that feeling. So the box was moved from initial location to the final location horizontally, which means the displacement is a vector which points to the right. That's a vector. The magnitude of this vector, the length of this vector, is represented by that variable s with two vertical bars. Length of displacement. Now, the normal force, how does it point in this particular situation? How do we call the direction? Normal force is perpendicular to the surface. That is correct. That's the general definition of the direction of the normal force. But the direction of the normal force might depend on the orientation of the surface. If the surface is horizontal, how does the normal force point? To describe a direction of a vector, we use exactly the same words we used before: left or right, up or down, north or south, east or west. So how does the normal force point? Up. So now, do you see the angle between the normal force and displacement? I do. This is the angle. What can you say about the value of this angle? Let's call it theta. Can we assign any number to this value? 90. Now, if you have a calculator, you can actually calculate the cosine of 90. What number do you get? 0. So if you're multiplying three numbers, one number, which represents the magnitude of a force, second number, which represents the length of the displacement, and 0. What do we get? 0. It doesn't matter if the force is strong and displacement is long. Normal force doesn't do any work in this particular situation. 0 joules. 0. This is how we apply this definition of work. We have to see the angle. If we don't see the angle, we just can make a mistake. Well, work in physics is not work at your workplace. For example, if you hold a heavy object still, you don't do any mechanical work because there is no displacement. However, you feel it's kind of difficult to hold it. So when we say this word work, we always mean a specific calculation behind that. This is the work in mechanics. Even if we feel like we're doing work, in reality, we don't do mechanical work. When, for example, nothing is moving, you can push on the wall very, very hard, get sweaty, you know, but still you're not doing any mechanical work. You still spend energy, of course. Yeah. Why? Well, because the blood is moving inside you, and that motion is required some energy. So mechanical work is a number, and that number can, as any number, can be positive, 0, negative. And that number only depends on this angle, because the magnitude of the force is never negative, magnitude is never negative, displacement is never negative. So if you have a situation when the angle is acute, between 0 and 90, that force does positive work. When the angle is between 90 and 80, that force does negative work. When the angle is 90 degrees, that force, even if it's acting, doesn't do any work. That's it. Now let's calculate work done by force of gravity because, well, it's important, and we can do it because gravity is a constant force. In this example, well, we shoot the ball and it lands somewhere, or it doesn't matter, maybe it keeps flying. There's the initial location, there is a final location. What's important is force of gravity acting on this ball always points down and has exactly the same magnitude, so it's constant. Force of gravity is constant. Hence, we can apply the definition of work for the constant force. The magnitude of the force of gravity equals mg. Well, the displacement is a vector. It starts at the initial location, it ends at the final location. This blue arrow represents the displacement. And for now, all I can write is delta S or delta R times cosine of the angle between the force and displacement. And this angle is a part of a right angle triangle. In this triangle, the hypotenuse represents the magnitude of the displacement. This is the angle. And we know from the geometry, if we're multiplying hypotenuse times cosine of the angle, we should get the length of the side adjacent to this angle. This, we can call it L. Yeah, that's what it should be from geometry. However, we also can see from our picture the same length also equals the difference between the initial height and the final height of the projectile, the initial y coordinate and the final. That's what it is. So that gives us very convenient equation for calculating the work done by force of gravity. We just have to replace this product, delta R times cosine, delta R times cosine, with the difference, because they are equal to each other geometrically. We used one specific example to derive this equation, but for any possible situation, we can repeat the same calculation again and again and again and again. We always get the same result. What's going to happen if instead of moving down, object moves up? In that situation, the initial height is lower than the final, so this difference will be negative, which means when object being moved upward, gravity does a negative work on it. When object moves downward, gravity does positive work. When object moves horizontally, gravity doesn't do any work like normal force, because the height doesn't change, same height, initial and final. If I move the object upward by my hand is doing positive work. There's a force, we call it normal force from support, and that normal force actually now doing work, positive work. All right, that's an equation. Don't do that, I just said it. It's going to be equal to 0 when object in a horizontal motion, gravity doesn't do any work because the initial height and final height are equal to each other, or we can employ the same type of reasoning we used for normal force. Force of gravity points down, displacement is horizontal, the angle between them is 90 degrees. So no matter how you think about it, when object moves horizontally, force of gravity doesn't do any work. Let's do this. We have time. Please read it. And I'm going to switch to the next slide where I'm going to solve this problem. It's about work you're doing. So the applied force makes it move. Of course, that's not the only force acting on this object. There's force of gravity, there's normal force, frictional force. And every time when we say this word force, that means draw a Freebody diagram, show all your forces, nothing new. And we used to say a rule, every force has a source. Now, there's a different rule. Every force does some work. Sometimes could be 0, like normal force or force of gravity for the horizontal motion. Sometimes could be positive, like in this situation. And sometimes could be negative, because friction, for example, is opposite to displacement. So the angle will be 180, and cosine of 180 is -1. Friction does negative work. So we will calculate all works here. For now, we just need to calculate work from applied force. And of course, it's about the drawing a picture. The box was here, now it's there. We need to see the displacement, because if we don't see it, we will not be able to say anything about the angle between the displacement and the applied force. How does applied force apply this way? And this angle, well, actually, I prefer using equal angle, but this one is equal to 60 degrees. Now, if you look at this picture, you have a tendency to say that the angle between the displacement and the force is equal to what number? What's 180 minus 60? What's 180 minus 60? 120. Very often people say that. That is wrong. A common mistake. Because if you want to measure an angle between two vectors, we have to redraw vectors from the same point first. That's what the direction is. This vector points to the right. This vector points like, I don't know, southeast. And this variable is the angle between the force and the displacement. And this is 60. Now we're done. Yeah? Now we have to apply the equation straightforwardly. The magnitude of the applied force is 14. The magnitude of the displacement is 2 meters. And the angle we have to use for calculating the work is 60. Just remember that. This is how we measure angles. The correct way to measure angles between two vectors is first to draw the vectors from the same point. I don't know what it is. 28 times cosine 60. Cosine 60 is so 14 joules. Work done by friction. Well, the friction is a tricky force because when object is traveling in a complicated way, for example, like this, velocity constantly changes its direction. But friction, kinetic friction, always opposes the motion. So kinetic friction always points opposite to velocity. When velocity changes direction, kinetic friction changes direction. So it's not technically a constant force. What's good about it, it keeps the same magnitude. So if I move an object along complicated path, right here velocity points tangent to the trajectory, that's velocity, which means my friction, kinetic friction, should point opposite to it. And here at this location, new velocity, new friction, but the magnitude of the force of kinetic friction still is equal to the coefficient of kinetic friction times the normal force. And as long as we don't change, the normal force, if normal force remains constant, hence magnitude of the force of friction remains constant. So what do? We break the whole path in tiny, 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 tiny intervals. Within each tiny interval, we can treat frictional force as constant. And for each tiny interval, we can calculate the tiny work done by the frictional force, which is supposed to be equal to what? It's supposed to be equal to the magnitude of the frictional force times the magnitude of that tiny displacement times cosine of the angle between these two vectors. And this angle always equal to 180 degrees, no matter where we measure it. Velocity, friction, 180. And cosine of 180 always equals -1. So -1 times, well, the magnitude of the force of friction equals coefficient times normal force times tiny displacement. What do we do now? Now we do this. Remember what does it mean, this symbol? The sum. We calculate the sum of all those tiny works together. What does it give us? This is the same number for all of them. This is the same constant for all of them. This is the same number for all of them. We just have to add all our tiny displacements together. And that gives total length of the trajectory. So this is how we can always calculate the work done by friction. It is always negative. It depends on the length of the path. For example, if I take this box and I move it in a circle and I bring it back to initial location, total work done by gravity will be 0, because initial height and final height is the same. But if I take this box and I slide it on a table like this, friction does work. And it's related to the length of this path. That's the difference between force force of friction and force of gravity. For the force of gravity, if we use complete path, the total work is 0. Forces like that have a name, conservative forces. For the friction, complete path, the work is not 0. Forces like that have a name, non-conservative forces. But we're going to talk about friction, basically, as an example of non-conservative forces. So this is how we always can calculate work done by friction. Always negative. Depends on the length of the trajectory. 3 minutes, more than I need. Again, we pushed the box. We supplied certain speed, and eventually the box stops. Final speed is equal to 0. Well, we actually solved the problem. I just don't have the number in mind. So friction points to the left, normal force points up, force of gravity points down, acceleration points to the left, and what we need to calculate is the work done by friction. And we already know it has to be negative. It has to be equal to the coefficient of friction times normal force times the length of the trajectory. So it's going to be equal to -1 times coefficient 0.4 times normal force. Normal force in this situation has the same magnitude of the force of gravity, and we had it before, 400 newtons. So the only variable left is the length of this path. But we found it in a slide number 6, I think. Thank you very much. Yes. Can you show me what the syllabus say?
I sent you the picture. I don't need to sign in for their attendance, no?
No.
Okay.
Does your picture have your name and BOID?
Yeah.
That's it? So first of all, I can make a conclusion that you've been late today.